Having already discussed how numbers can be represented as bits, we can now talk about text. First, though, it will help if we lay down some terms for quantities of bits. So, first off, certainly you're familiar with the term byte. The trouble is that the popularly understood definition for byte is actually not really correct. Most people think that a byte is always 8 bits, but in actuality, a byte is the size of an individual cell of addressable memory. All of a computer's memory are divided into little buckets, and each one of these buckets is an individual byte of memory. The first address in memory has the address 0, the next byte has the address 1, the next one has the address 2, and then 3 and 4 and 5 and so on. Now, it's true that virtually all systems created in the last few decades have 8 bits per byte. 8 has become the de facto standard. However, if you go back to the 1970s and earlier, you'll find there are many systems that used something other than 8. There were systems that used 7 bits per byte, one that used 13, and another that used 27, and all sorts of different numbers. In the end, system makers settled on 8. What's so great about 8 bits per byte? Well, there's no hard and fast reason to use 8 other than it's not too big, it's not too small, and it's a nice power of 2. It's also nice that 8 is a multiple of 4. Remember, when we translate hex to binary, each hex digit corresponds to 4 binary digits. So if we want to represent an 8-bit byte, we always just need 2 hex digits. As a practical matter, defining a byte as always 8 bits isn't really harmful, because basically the world has settled on 8-bit per byte machines, and it looks like that's probably never going to change. On the other hand, it's a good thing to know, and if you want to annoy people with pedantry, you can always insist that the proper term for 8 bits is octet. The term octet always unambiguously means 8 bits, no matter what system we're talking about. To make it easy to talk about large quantities of bits, we have prefixes like kilo. The problem is that these prefixes are actually ambiguous. Most people think of a kilobyte as being 1,000 bytes, or 10 to the third bytes, but the original technical definition of kilo was not 10 to the third, but rather 2 to the 10th. And 2 to the 10th is 1024, not 1000. The same confusion applies to the other prefixes like mega. Most people think of a megabyte as 10 to the 6th, a million bytes. The original technical definition, though, was a power of 2. It was 2 to the 20th, which is 1,048,576. Again, the prefix giga has the same confusion. A gigabyte is commonly thought of as 10 to the 9th bytes, or 1 billion bytes, but the original definition was 2 to the 30th, which is 1,073,741,824, some number you'll never remember. Beyond gigabyte, we have the less commonly used prefixes terabyte, petabyte, exabyte, and zettabyte. And again, notice the pattern. The popularly held definition of these prefixes is a power of 10, which is a multiple of 3, but the original proper definition of these prefixes is in terms of 2 raised to a multiple of 10. In recent years, people have finally tried to rectify this ambiguity by introducing new terms to explicitly mean the definitions in terms of powers of 2. In this new system, the old prefixes, kilo, mega, and giga, and so forth, they should be used exclusively when you mean some power of 10. When you want to talk in terms of powers of 2, you use a new set of prefixes. Instead of kilobyte, you say kilobyte, and instead of megabyte, you say megabyte, and instead of gigabyte, you say gigabyte. In common speech and casual technical discussions, these terms haven't really caught on. People are still very much in the habit of using the old familiar terms. These new terms tend to only get used in really formal discussions, like, say, in some very technical document. Now, it's most common to talk in terms of kilobytes and megabytes and gigabytes, that is, thousands of bytes, millions of bytes, and billions of bytes. In some contexts, though, people use the terms kilobit, megabit, and gigabit to refer to thousands of bits, millions of bits, and billions of bits, respectively. The distinction is important, of course, because a byte is 8 bits. So if someone says kilobit and you assume they mean kilobyte, well, you're off by a factor of 8. You should be especially careful when these terms are abbreviated. The convention in abbreviations is that a lowercase b should mean bit, whereas an uppercase b should mean byte. And just to be clear, the case of the other letters doesn't matter. So the K here can be uppercase or lowercase, but either way it just means kilo. Unfortunately, many people are sloppy with these abbreviations, so very commonly you'll see a lowercase b when they meant an uppercase B or vice versa. Strangely, though we usually talk in terms of bytes, there are some areas where it's more common to talk in terms of bits. So for instance, when we talk about, say, hard drive capacities, we almost talk in terms of gigabytes, not gigabits. However, it's the convention when talking about throughput, such as the bandwidth over a network, that we usually talk in terms of bits, not bytes. So when talking about, say, the speed of an internet connection, we usually talk in terms of megabits, not megabytes. To my knowledge, there really isn't any explanation for this practice, it's just the tradition.